Hello, I'm Jessica Russ, and I'm presenting my Intro to Materials Science final project. I've chosen to do my project on LCD screens. LCD screens are used in a variety of applications, ranging from calculators to laptops, to display screens to tablets, to everything in between. LCD stands for liquid crystal display. The product makes use of said liquid crystals and polarization to produce images. The first viable mass-produced liquid crystal for LCD screens was 5Cb, created by George Gray from Hull University. It was viable because it was polar, and thus could be manipulated by electrical currents to easily control the screen's output. These at the time new LCDs, and more modern ones too, are much more efficient than their CRT predecessors. Going further on liquid crystals specifically, they are considered between liquid and solid in terms of their state. Of the different possible types for LCD screens, twisted nematic screens, which I'll cover more later, use cholesteric crystals. These crystals are nematic crystals that are chiral, and they stack on top of each other to form a helix shape. Typically, other LCD screen types use somatic or nematic crystals, which all align in one direction. An example of another type of liquid crystal are thermochromic crystals, which are used in mood rings and other products where their color changes with temperature. The main principle behind how LCDs work is polarization. Polarization is when light is blocked in a way that limits the wave to only one direction. This can be seen with the diagram on the top right, where light is being blocked so only the vertical wave can pass through. LCD screens make use of two polarized films set at 90-degree angles. As another example of polarization, it is also used with sunglasses or camera lenses in order to limit the negative effects of sunlight. Next up is the basic structure of an LCD. They use a backlight of some sort, followed by two polarizing sheets sandwiching the liquid crystal layer. Electrodes are also included on either side of the liquid crystal to manipulate its structure. Colored films or another source of colorization is included either on top of the backlight or in front of the liquid crystal. There is also a final glass layer on top to protect the inner components. Starting on specific screen types, first up is twisted nematic as seen here. Twisted nematic screens make use of the helix-shaped cholesteric crystals as mentioned earlier. When no electricity is flowing, light is allowed through the screen, as the crystals bend at 90 degrees to allow it to pass through the second polarized layer. When voltage is applied, the crystals untwist, causing the light to go straight and thus be blocked by the polarized layer. Compared to the later two screen types, twisted nematic screens are the cheapest to manufacture, and they're also the oldest. However, they also have worse viewing angles and color contrast. 5CB is an example of a twisted nematic LCD. The next screen type is vertical alignment, or VA. VA screens have their crystals be perpendicular to the polarizing layer, so the screen lets no light through by default. When a current is applied, the crystals turn to being parallel with the polarized layers and thus let the light through. These screens have better color and viewing angles than twisted nematic screens, and have higher resolution blacks and refresh rates than the final screen type, which is in plane switching LCDs, or IPS for short. Crystals in IPS screens are held in the same plane as the first parallelized layer in such a way that the screen is black when no current is applied. Once electricity is flowing, the crystals spin 90 degrees to let the light through. These screens typically have the highest color resolution of the three types, but have slower refresh rates than VA screens. Next up is the experiment. For the experiment, I showed how polarized light cannot pass through a polarized lens that is aligned so that the waves are perpendicular to it, as shown here by it being black. I showed this on each of the LCD screen types I covered, starting with VA, as shown here via TV. TVs are often VA-type LCDs because they provide deeper blacks and color contrast. Now seen here, when I put the plastic wrap between the TV and the lens, it breaks up the polarized light from the screen so it can now go through the lens. Next up will be an IPS screen. This will be shown via my phone. Most modern phones make use of OLED screens instead, but slightly older phones, like mine, make use of IPS screens. You can see me here repeating the same process as with a TV screen with the plastic wrap. The final test is with an older calculator, which will be shown in, there we go. So this is a twisted pneumatic screen. It's harder to see on camera, but the lens does block the numbers from being seen, and the plastic wrap does make them visible again. Here are my sources, and I missed one. It went through very quickly. Thank you for your time.